Okay, so next one is feedback amplifiers. So first we'll see what is the use of amplifier. So amplifier is a circuit that basically amplifies the input signal. Okay, and then feedback amplifier means we are providing some feedback connectivity from output to the input so that we can increase the performance of the amplifier. So this is the block diagram of feedback amplifier. So Vin is the input signal, V naught is the output signal. So what we are doing is input signal that needs to be amplified is given to the mixer network or mixer device followed by amplifier. Okay, then from amplifier we are obtaining the output. So in feedback connection, what we are doing is we are taking some part of the output and that is being given to the feedback network beta. So beta is the feedback network. So from a feedback network we are getting one more signal called feedback signal VF. So that is again been given to the mixer. So I can expect two signals at the mixer. First one is Vin, second one is VF. Then I'm getting the signal from mixer as Vi. Okay, so this is the signal that basically given to the amplifier. Okay, so if the feedback signal Vf is in phase with Vin, then it is called as positive feedback signal. If Vf is in phase with Vin, then the feedback should be called as positive feedback. Otherwise, if the Vf is out of phase with Vin, means it has to be called as negative feedback. Okay, next we'll check one block diagram for the negative feedback network. So negative feedback network means, this here, A means amplifier, B means feedback network, V means input signal that needs to be amplified, V naught means it is the output, then Vi is the signal that is obtained from the mixer network. So this is the mixer network. Okay, and this negative symbol indicates that it's a negative feedback circuit, means Vf is out of phase with Vin. So what happens is gain means it is the ratio of output voltage by input voltage. So if I take only A, then it has to be called as gain without feedback, or also we can call it as open loop gain. Similarly, if I write AF means this F indicates gain with feedback or closed loop gain. So we know that A equal to V naught by Vi, therefore I can write V naught equal to A into Vi. I am calling it as equation number 1. Then I am writing Vi equal to V in minus Vi. Vi equal to V in minus Vf. So this is my Vi. Vi means it is the signal obtained from the mixer. So since it is negative feedback network, I need to write it as Vin minus Vf. Same thing I have written over here. Vi equal to Vin minus Vf. Then that will be equal to Vin minus beta into V naught. What is Vf? Vf is the feedback signal. So Vf I replaced by beta into V naught. Vf I replaced by beta into V naught. I am calling it as equation number 2. Now what I am doing is I am substituting equation number 2 in equation number 1. So V naught equal to A into Vin minus beta V naught. Then after rearranging the terms, I am getting AF equal to V naught by Vi equal to A divided by 1 plus A beta. Thus the negative feedback reduces the gain by a factor 1 plus A beta. How exactly it works, that we will check later. Okay, so next is the properties of negative feedback amplifier. So first property is it reduces the gain, then desensitize the gain, reduce the non-linear distortion, reduce the effect of noise, control the input and output resistances, extend the bandwidth of amplifier. Then advantages: stabilized gain, higher input impedance, lower output impedance, increased bandwidth, and reduction in noise. So next we'll check one voltage series feedback amplifier. So in this we can find the different components like the previous one. A is the amplifier, then beta is the feedback network. Okay, so next is Vin. Vin is the actual input that needs to be amplified, and V naught is the actual output after amplification. Okay, so in between I can find ZIF. ZIF means it is the uh, input impedance with feedback. Zi means it is only input impedance. Similarly, Z0 means output impedance. Z0F means output impedance with feedback. Then output voltage we are checking across one load resistance RL. Then again VF will indicate the feedback signal that is being obtained from the feedback network. So I have one graph here. It is frequency versus gain. I can find two types of curves here. So this is the first one. So in this first one, right, I am showing it as A0. A0 means it is the gain without any feedback, or even I can call it as open loop gain. So gain is bit higher here. Okay, this is the first curve, and I am having one more curve like this is the second one. Okay, second one I am calling it as A0F, gain with feedback. Okay, so if I compare first curve with the second one, what I can observe is in the first one gain is more, in the second curve gain is bit less. A0F is less compared to A0. Okay, so I am taking 2 points here from first curve, F1 and F2. The difference between F1 and F2 I am calling it as bandwidth. So bandwidth means it is the range of signal frequencies that needs to be transmitted for a longer distance without any interference. Okay, so similarly I can check with second curve, and similarly I can take 2 points, F1F and F2F at 0.707. Okay, so in this, if I take the difference between F1, F2, F2F, I can observe that from the second curve I am getting the more bandwidth. Okay, I am getting more bandwidth from the second curve. But if I check the first curve, or if I take the bandwidth from the first curve, it is bit less compared to the second one. So what happens is, with the feedback network we will have control over the gain. So this second curve will indicate that it is the gain obtained after the feedback. So what happens is, gain will be reduced, at the same time we are increasing the bandwidth. Okay, so BWF is more compared to BW. So this BWF is the bandwidth obtained after the feedback. Okay, this BW is bandwidth without any feedback network. Okay. So next is again we are checking for gain. Gain equal to A equal to V naught by Vi without any feedback. Gain with feedback I am writing it as V naught by Vin. Then feedback factor beta equal to Vf by V naught. Then V naught equal to A into Vi. I am calling it as equation number 1. Then Vi equal to Vin minus Vf. Then Vf is nothing but beta into V naught. Then I am getting expression for Vi as Vin minus beta into V naught. I am calling it as second equation. Then again I'm substituting equation number second in equation number 1. Then I'm getting the expression for AF as V naught by V equal to A divided by 1 plus beta A. Thus what happens is the negative feedback provides the higher stability. Higher stability means we can have control over the gain. Similarly, I can increase the bandwidth. Then we have one relationship between gain and bandwidth. So gain into bandwidth is a constant parameter. So what happens is, if I don't use any feedback network means I'm getting gain as maximum. At the same time bandwidth will be very less. So to increase the bandwidth, what we are doing is we are using the feedback network. So using feedback network, what happens is we will have control over the gain. So as gain reduces, automatically the bandwidth will increase. So that is one of the main advantage of using feedback network. Means we can increase the bandwidth. So next is gain stability with feedback. The overall gain with negative feedback is given by AF equal to A divided by 1 plus beta A, differentiating with respect to A. On both the sides, I am getting it as dfa by dA equal to 1 divided by 1 plus beta A whole square. By rearranging the terms, dAf by dA equal to AF divided by A into 1 plus beta A. dAf by dA equal to 1 divided by beta A into dA by A. This I can also write it as divided by 1 plus beta A, 1 divided by 1 plus beta A dA by into dA by A, 1 divided by 1 plus beta A into dA by A.